The periodic table, the cornerstone of chemistry. Obviously, the better ones are in colour, and the even better ones are interactive. I mean, look at this, it's just beautiful. And Google Chrome's also amazing. But how did it come about? Let's take a look. We start with Plato, a very famous ancient Greek philosopher who believed that the elements were earth, fire, water, wind, and heart.
By your powers combined, I am Captain Planet!
Okay, so maybe not the last one. Skip forward 2 millennia, and this man, Henrik Blond, like any self-respecting chemist, decided to distill his own urine. He found a glowing white substance, which he dubbed cold fire. But he decided to keep this secret. Until 1860, when an Anglo-Irish, up the boys, scientist named Robert Boyle rediscovered phosphorus. Why did he have phosphorus in his urine? Later, a French chemist by the name of Anton Lavoisier would define an element as something that cannot be broken down into simpler substances, and for this he gained the name the father of modern chemistry, which is just the coolest name. Based on this definition, oxygen, nitrogen, hydrogen, phosphorus, mercury, zinc, and sulfur were defined as elements. And here you can see an early version of his periodic table. Whilst well thought through, Lavoisier's ideas weren't accepted by the science community at the time, which you'll see is a running trend in this video. He also believed light was an element, along with something he called caloric. But come on guys, when would light ever be matter? That's so silly. Next came John Dalton, who is also famous for his model of the atom. He based his work off 2 other Frenchmen, one named Dulong and the other named Petit. With their work, Dalton was able to calculate atomic masses, and this is how the Dulong-Petit model works.
The Dulong and Petit law says that the molecular heat capacity is equal to the mass times the specific heat capacity, and because of this, there's a long process, and eventually you end up with the molecular heat capacity is equal to 3 times R, R being the gas constant, which I've just made 3 decimal places for ease, and then you can rearrange this and you get 3R over C is equal to the molecular mass. And if we use iron as an example, which has a molecular mass of 55.84, you do 3 times 8.314 over 0.450, which is iron's specific heat capacity, and you get 55.427. Now, obviously, there is some difference in between these numbers, but don't forget that in modern periodic tables, this is made using averages of isomers. Following on from this, they realised that the atomic weight times the specific heat capacity was about 6.4. They had answers ranging from 5.7 to 6.7, but 6.4 was the most reoccurring, so they decided to use that. And it doesn't matter that it's an approximation, and you'll see in a minute why. So you can rearrange it and you get mass is equal to 6.4 over the specific heat capacity. If you use the values for zinc, which are here, you get about 67. And again, because this is an approximation, this is also an approximation. So then you use this equation, which is atomic weight equals valency times the equivalent. The equivalent is just how much mass of an element reacts with 1 gram of hydrogen. So in zinc's case, it's 32.5. So the valency of zinc is equal to 67, which we worked out here, over 32.5, which is the equivalent. And you get 2.06. But because you can't have 0.06 of an electron, it's 2, okay? And then because you know it's 2, because it can't be anything else, because this is so close to 2, but it can't be a decimal, you do 2 times the equivalent, 32.5, which you know is true because you've worked it out experimentally, and you get 65. Which is the atomic weight of zinc today.
Comes this man, Johann Wolfgang Dobereiner, who classifies elements into groups of 3 based on similar properties they exhibit and calls it his triad law. Building on this is French chemist Alexandre-Émile Beguier du Chancota, who realizes that elements listed by their atomic weight show similar properties at regular intervals. So he creates the telluric helix, named after tellurium. And I mean, look at that. That is just horrifying. Tellurium at its center. This is just the thing of nightmares. Then comes the big man himself, Dmitry Mendeleev. Said he made his periodic table after playing Element Solitaire on a train ride home. And if you can't tell, it's based off the card game Solitaire, and if you can't tell more, I'd suck at this game to an unreal degree. This is me playing in the background, and I just don't know what I'm doing. Here you can see his prototype table with gaps in it, and it's because of these gaps Mendeleev was called crazy, and the scientific community once again didn't accept his ideas, until his gaps started showing up. And eventually in 2010, everyone's favourite state, Tennessee, got its own element, and this filled up Mendeleev's table. This meant any newly discovered elements had to be put in the lanthanides or actinides stages of the table. There you have it. I hope you enjoyed the video. Be sure to like and subscribe, and feel free to join me next week where we'll be going over the chemistry of climate change. Bye.